you, Fabian, for the introduction. And hello, everyone. My name is Mehmet Mercangöz. I'm coming from London. I'm with Imperial College London. My title is ABB Reader for Autonomous Industrial Systems. And actually, I was with the company ABB for quite some time before joining Imperial College, working with their research and development organization. You might recognize from my title there, Autonomous Industrial Systems. Even though I'll be talking about making machine learning models useful in industrial manufacturing, I'll start my talk by giving some motivations for why autonomy actually will be interesting for manufacturing as well. I will then gradually switch from those topics to some examples of really how we can use machine learning for manufacturing applications. So I claim industry needs to become more autonomous, and I want to justify this based on some evidence. Towards the end of the pandemic, when the economies were picking up, we have seen many cases where actually we were running into problems with our supply chains, with the way we will run manufacturing processes. Here I have one example from Canadian oil sands operations, where they were claiming that they were not able to find workers because they had laid off these workers and they weren't willing to work for Canadian oil sands operations anymore. The workers wanted to find other companies which they thought would be more stable jobs for them. This is maybe what we have. You might think this is this point in time where we have many things happening. But in fact, actually, when you start looking at the projections of the population and the demographics development for the future, you will see that the working age populations are going to be dropping quite quickly in the not so far future. And in some countries, like in Japan, actually, this is already happening, and there is an acute shortage of workers. So people are looking into how to make things autonomous. And that's one perspective, shortage of labor, but we have seen also many companies investing in autonomous solutions with other, let's say, considerations. I'm not going to go into all these details on this slide, but this has also aspects regarding boundary conditions, I call it, in how you will envision how you will build things. And in the context of manufacturing, when you consider factories today, we have a lot of space, a lot of equipment, a lot of energy consumption associated with manufacturing operations that are there for the people, so that they can operate the machines, they can exit if they needed to exit, or there is enough space, there is ventilation, there's lighting and all that. And these can be reimagined in new factories if we could operate these facilities without so much human labor. So, and if we want to look at how we can actually run these systems without human labor, we have to look at various aspects. So we have to look at what humans do with their perception. So we have seen many applications of machine learning actually already in these directions to replicate or do to a certain extent what humans do with their perception. We have to be able to do what humans contribute using their cognitive skills, understanding, analysis, decision making, and also with manipulation, what humans again do in order to run these facilities, run these systems. And we see many examples of maybe robots doing one thing or other if you think about manipulation, but also you have to see this over the life cycle of operations. So there is an aspect of maintenance, there's an aspect of continuous improvement and so on. And when you consider these aspects, actually there are other tasks, other capabilities that come into the picture where we have to do technology development to be able to do these things also without depending so much on human input. So I'll be talking a little bit about the decision making and understanding and let's say considering human cognitive input in this direction. And here, when we start now thinking a bit not only in autonomy, but also what else we can do when we are working with these systems, and obviously we can also improve the performance of operations if we are going to utilize similar technologies also in tandem with people. And this also goes towards the same objective of being able to avoid labor shortages, because it will allow us to be able to do more with maybe fewer people. This, of course, will require humans to be in contact, in interaction with these algorithms, intelligent systems, and so on. And this interaction actually has also many dimensions. We tend to look in industrial operations in these control systems using this automation pyramid, considering different hierarchies in the decision making that is happening. And when you look at actually how these systems can evolve in the future, we see many different forms of interaction. Then you might, for example, be familiar with an autonomous car and a driver that's holding the steering wheel, sort of ready to take over in case the autonomous system fails. Actually, we will have many different forms of interaction. We will have continuous, actually, collaboration of a person working with an autonomous system. We will have people giving orders to autonomous systems, or even autonomous systems giving orders to human beings when we are actually working with these systems together. So gradually moving to the topics that I'll be talking in more detail today, when we have these systems, we obviously can do actually beyond just substituting human input. We can actually do superhuman things. This especially comes into the picture when we are dealing with things that are happening very fast. And this is already the realm of automation, already the realm of, let's say, control systems and so on, where the response time of a human being is not able to actually handle such a situation. And also it's the same thing when we are dealing with very complex systems. So if you think about scheduling the flight operations of an airline company, this is not something human cognition can deal with. This has to involve, again, algorithms and complex systems. And this is where, let's say, I'm bridging now to what we can do with the similar technologies that we are working on to make things autonomous, also to improve, let's say, performance and operations in manufacturing settings. I have collected my slides, or the remaining slides in this talk, based on an important metric for manufacturers, and this is overall equipment effectiveness. And it's a very good metric because it combines many important aspects of operation into one metric. And to talk a little bit about this metric, it considers availability. So this is about how much of over a given period of time your machinery was actually running and operating. And then we have performance efficiency. So over that time, now if you look at the time that machine was operating, what kind of productivity that machine was achieving. So how many products was it able to produce over a given time range. And then finally, we have to consider quality of what portion of those products that machine produced is actually possible to be sold to customers. And eventually, the multiplication of all these factors give you the, let's say, sellable output that your factory has produced. And in manufacturing environments, what you will see is that you will have actually not a single machine. You will have series of machines typically organized in sequence in a manufacturing line. And you might have actually parallel lines operating together, forming large factories. And in principle, it's possible to actually project this thinking to these lines of machines and to factories and even to multiple factories of an organization. So it's a very, very nice metric. What I will do now, I'll give some examples for each of these: availability, performance, and quality, of how machine learning can be used, how it can make a difference. And I'll start with availability. And I'll start talking about my favorite topic, which is process control. And here you see a signal that is gradually deteriorating. So what you are trying to, let's say, control there is actually getting more and more jiggedy. It's not stable. And so all these machines actually need to be controlled. So this is relevant for all of these machines. And what happens when you have actually such a situation? It could lead to a situation, let's say, maybe a thermal overload or something, or maybe a vibration level that might require you to shut the machine down. So it will lead to a loss of availability. So during that time, when your machine is not running, you will not be able to benefit. You can also consider that if you are not able to control your machine, if you have so high actually fluctuations in your variables, and if you want to operate close to these thermal limits, let's say, because that is where you will actually produce the most output, it will prevent you from being close to that, because you have to take into account these variations and take a certain margin off of those limits to make sure you don't violate them. So this is a challenge. And how do we address these? Let's say if you want to put together really high-performing control solutions, one approach that we utilize is what we call model predictive control. And here, actually, we have a system model. And using this model, we are able to create predictions. So here you see, let's say we have some boundaries and we have a trajectory that we can generate using these system models. And we can actually check if we are violating any bounds when we generate these trajectories. We can also check if we are ending up with a certain objective that we want to achieve. So in this case, you see that we are violating a bound, and we are also not ending up in the objective that we want to achieve. So next, what we can do is actually we can vary the decision-making capabilities in our system. We can change the inputs to this system and generate other trajectories. And we can generate a trajectory that actually doesn't violate these limits and actually ends up on target. So if we can create these trajectories, solving optimization problems using these degrees of freedom that's available to us, we can actually determine how we can run the system. And with model predictive control, what we do is we implement the nearest actions and we repeat this process. So this timeline actually keeps shifting. We get new data, we run new solutions, and we do this. But at the heart of this, to be able to do this, we have to have this system model. So traditionally, we build these system models using domain knowledge. We have engineering equations. We have all these books that are out there, the fundamental principles that we can use to put together models. But what we see is that both these systems change in time. So whatever model we have actually doesn't last for a long time in representing the system behavior. But also for, let's say, the domain where I am at, chemical engineering, when we scale these systems actually building the design principles, we end up with things that work, but most of the time we don't fully know what's really happening there. But we can collect information, and actually we can compensate for what we don't know using data-driven models. So we can actually combine these, make the best of both worlds. And this is something we are doing. And also we are looking at doing this in an autonomous fashion, so really looking at various model options, doing neural architecture searches and so on to put together models actually which could be used for these purposes. And this is also possible to utilize. In this example, it is from paper manufacturing to control, let's say, the operation of a paper machine in this case. Moving on to performance, now I want to talk about also another topic that came up in the keynote talks this morning, and that is going to be about actually the availability of data. And here performance can relate to really how well we are running this machine, how much energy it's consuming, how many products it's able to produce at a given time. So in this case, I'm showing you an example of a performance curve for a compressor. What we have seen working with these machines is that we are thinking we are generating a lot of data when we run these systems, but oftentimes of this, let's say, map that shows the operating conditions, you are operating in very narrow spaces. And operating in these very narrow spaces doesn't generate, actually, even though you can collect gigabytes, terabytes of data, actually there is not a lot of new information there. So we asked the question, how can we actually utilize machine learning models that are able to learn with fewer number of data points? Because let's say if we switch just a little bit to another operating point, with that information, are we able to update a performance curve? And how well are we able to do this? And in this particular example, we are able to generate the full map with only 20 points, actually, just 20 samples out of this, and we are able to generate a very, very good representation of it. Of course, the trick here is to have access to the right hyperparameters, to have access to the right kernel functions, and so on. And having those is a challenge, but if you have those specific for a certain machine kind, for let's say a certain physics that's behind this system, then actually it is possible to represent these systems with fewer number of data points, which we have seen. And I have another plot for showing the other, let's say, the speed representation of the system as well. You can actually, once you have those performance characteristics, what you can do is actually you can do optimization. So here we have also shown this when we have 3 such machines running in parallel, we are able to actually reduce the energy consumption. So here you see the time and energy consumption, aggregated energy consumption, and this will be the base case. And out of that, using these learning models and the performance curves, we are able to actually reduce this energy consumption significantly in this case. The final topic I'm going to talk about is quality. And again, this is something in manufacturing is extremely important. But in many manufacturing cases, actually, you are not able to influence the quality properties of a single unit that you produce. So this could be maybe in some cases, like an automotive case, if there is a problem with the paint or something with a single unit, you might take it out of the production line to do some extra work on it. But in other cases, let's say if it's a bottle of a beverage and the label is not printed right, you will not go there and redo the label. So here, the control approach is not to control the individual products, but what you do is actually you monitor the operation and you look for anomalies, and then what you try to fix is the source of these anomalies. Where actually was the problem coming from that label was not attached properly to that bottle. So that's what you are after. But the challenge is you're working with actually very large number of measurements. So in this case, again, I'm going to show you a case from chemical engineering. That's where the data is coming from for me. And here in this case, it's a chemical process with close to 100 measurements in this case. And what we have done is we compared traditional multivariate monitoring solutions with deep learning based alternatives. And what we have seen is we were able to generate actually significant improvements in selectivity. So we were able to detect the anomalies, the issues, much more precisely compared to the baselines when we use these methods. And we were also able to actually tune these solutions so that we could go back and figure out where these, let's say, aggregate deviations were coming from. And also when we did it using deep learning, we were able to make it much more precise. So it tells us exactly from which measurements actually the issues were coming from. So you can focus on where those measurements were attached to in the particular part of your production process and go there and investigate it and indeed do maintenance or replacement so that the quality issues will not happen. So overall, the tools we have in my lab, what we are using mathematical modeling, optimization, control, and analytics. But on top of this, what we are trying to do is really to bring more autonomy, to create adaptive systems, system architecture optimization, and also verification of such end-to-end solutions so that we know that they will be safe to operate and so on. So with that, I thank my budding group. So I didn't start long ago. It's a young group. But with that, I'll conclude and will be very happy to address questions if I still have time for questions. Thank you.
Thank you very much, Mehmet. So we've got around 4 minutes for questions. Any questions from anyone?
Yeah, the question is about optimization and do you have enough data to do optimization? Because in an industrial plant, you cannot do experiments, right? So then you are dependent on observational or past data, but that's biased, so how does it work?
You could actually do some experimentation. It will take time, of course, especially if it's going to require that you take certain operations offline or stop production during that time. But if you see that there is going to be a certain rate of return on that stoppage, because you will use that information to build models with which you can do optimization, then you could actually convince the operator of such plants to do experiments. And we do optimization, so this is actually and there is also useful data as well. The question is really how much improvement can you bring in? So the more information you have, the more improvements you will be able to bring in. And I think where we are starting from, in many operations, there is room for doing optimization, even with, let's say, historical data, what might be there and so on. And using, of course, some judgment on the operations. And when you bring it together, you can get started. And you can also devise then procedures that will help you to collect useful data and search for, let's say, where this data might be. And I'm very excited. There are a lot of developments in areas like safe learning, where you can actually direct that exploration process within that industrial environment where you know that you have to be safe, where you shouldn't violate, let's say, constraints, and exploit that really to collect the new information and then move your system that way.
Maybe one last quick question. I'm coming.
Thanks. As there are many plants in manufacturing which are quite old, I would say 30 plus years old, with very old control systems. What is, in your opinion, the prerequisite to start such projects in terms of getting the data, gathering data, optimizing the control system which are in the factory itself?
Mm-hmm. Old in this case doesn't necessarily mean something bad. I mean, if it's collecting, if the sensors are there, there will be information. And I have seen that there are many paths to, let's say, bridge that information and bring it to platforms where that information coming from sensors can be useful. The question is if these sensors are there. And in my experience, in most plants, that the essential information is present. So it really requires an initial motivation to get started with this and to have really a good idea on where benefits can come from. And in many industries where there will be significant benefits coming from these exercises, this is known. So in these sectors, there will be known optimization solutions. There will be vendors selling optimization solutions, regardless of how old, let's say, the manufacturing system is. And sometimes the older it is, the more interested they might be in actually implementing optimization, because they might have more room to actually improve things. The question is how applicable this is to every manufacturing process. There could be also processes, and there were cases where I have also encountered myself, where let's say, the margin for improving things is not so much, because that's how the system is built. So you have to run it the way it is. There's not so much extra space which you can then exploit to improve things. And sometimes the improvements could be not justifying the investment. That's a little bit where I'm basing my main motivation for the work in my research group is we see often the case where it might be an improvement 1%, 2%, and when you have that and when you look at the amount of PhDs you need to throw at that problem to solve it, it doesn't really justify in the end the returns. So the question is how can we reduce that mental burden, that domain knowledge burden and so on that you need to have in order to offer that saving. And if we can actually reduce that access or the threshold, then I think there will be many other cases where such improvements can come in, regardless of the age of the manufacturing system also. Thank you for the question.
Thank you, Mehmet.
Mm-hmm.